In this video, I'm going to talk about how we find the direction of an unknown force. I'm going to do it with 4 classic examples. This particular question has been a Oxbridge interview question, and any of these could be too, not because they're very difficult, but because they really get to the heart of understanding about moments in equilibrium. So with this one to begin with, the problem we're trying to solve is what direction is the reaction force of the wall on this bar at the hinge. So to clarify, does it go this way, to the horizontal to the right, sort of down to the right, downwards, any of these sort of 8 approximate directions. Now we can get into slightly more specifics, but approximately where does it go? The first thing we have to do to solve this is to label the forces that we already know. So we can assume that this is a uniform rod, and therefore it's going to have weight acting downwards. This is some kind of cable. It's going to have tension acting in that direction. Now, in order for this to be in equilibrium, there are 3 conditions that have to be met. One is the sum of forces to the right have to equal 0. The other is the sum of forces upwards have to equal 0. And the other is that the sum of the clockwise moments equals the sum of the anti-clockwise moments about any particular point. Now, those 3 equations all have to be satisfied, and they might help us decide which direction this is going to, the force here is going to be in. So I'm going to start off by considering this one here. So the sum of forces horizontally has to be 0. Well, this has no horizontal component, so it doesn't contribute. This one does have a horizontal component. It has a horizontal component to the left. That means that this third force must have a horizontal component acting to the right that's equal to the horizontal component of this, but in the opposite direction, so that we end up with a sum of 0. So it has to balance, the right one of this has to balance the left component of that. So we know that it's either going to be this, this, or this. It can't be any of the others because it has to have a rightward component. So we've used that one. Now, if we try and sum forces vertically, we don't actually know the relative size of this and this. So it could be that the weight of this is larger than the vertical component of T, in which case we'd need it to be up here in order to help this one balance weight. Or if the vertical component of T was larger than W, then we'd be imbalanced towards the top. So we'd need this to have a downward component in order to help weight balance the vertical component of T. But we don't know either of those, so we actually can't use this equation. So we're going to have to go to moments. Now, there are 3 points we could take moments about here, and sometimes we might have to try more than one position in order to get the information we need. If we try position A, that's useless for us because this force R, its line of action goes through A, and so it's always going to be 0. So instead, it's best to take moments either about B or C. I'm going to show you that we can do either now. So first of all, I'm going to do sum of clockwise about B equals sum of anti-clockwise about B. So I'm taking moments about there. If I consider the forces we have at the moment, weight, its line of action would go through B, so it doesn't exert any moment about B. So we can ignore weight. This one goes in an anti-clockwise direction around B. So that means that this must have a clockwise direction around B. That means it has to be this one, not this one, because that would be contributing to the anti-clockwise moments, and then this bar would rotate upwards. So we've established which one it is now. Now I said I was going to show you how we could do this with either of these positions. So we're going to pick C now. If we take moments about C, T has its line of action going through the pivot, so it doesn't feature in the principle of moments equation. B goes in an anti-clockwise orientation around C. Therefore, A must go in a clockwise orientation around C in order to balance the anti-clockwise moments. So we've established it must be in this direction. I've not actually said whether it's that way or that way, you know, whatever, but somewhere within that quadrant. Next problem. This is the classic sort of ladder up against a wall. We're often told to assume that the wall is smooth, which means it has no friction component, which means it has no component of reaction force, contact force that is parallel, which means that all of the force is perpendicular to the slope. We then normally assume that this is uniform, but it doesn't really matter for this particular problem. We have a force to the right, left, and a force downwards. And we're asked, what direction is the reaction force from the floor on the ladder? Well, if we go through the same things we've got here, if I consider horizontal, then this force here acts to the left. This doesn't have a horizontal component, so this must have a rightward component. So I've narrowed it down to either there, 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 there. Yeah, so those sorts of things. So this one is above the ladder, this is along the ladder, this is below the ladder, this is to the right, this is down below. Now I'm going to do some of vertical forces. Well, this one doesn't have any component in the vertical direction. This one is vertically down. So I know I must have an upward component. So it can't be that one and it can't be that one. It's one of these three. Now this is where people normally get to pick one of these, but they're not sure which one. And the next step is to take moments about a point. So again, I can take moments either about there or about there. I'll take this point to begin with. If I take moments about there, this force exerts a anti-clockwise moment. So I need to add in a clockwise moment from here to balance it. That means that I need something going this way round. So it has to be this one above the ladder. Not vertical, because we need to have a horizontal component to balance that, but not along the ladder, because if it was along the ladder, it wouldn't exert a moment about this point. So it's just above the ladder. Now, we could do it about this point similarly. That's clearly exerting an anti-clockwise moment, so we need a clockwise moment. That's that one. These two are very similar. You can work them out yourself. I'm going to give you a chance to sort of pause the video and try it. And now I'm going to do it how I would do it without sort of so thoroughly going through everything so quickly. Right, right, so it's got to be to the left, up, down. I therefore don't know whether it's up or down. I have to do moments. So I know it's going to be to the left, but I need to find out which of these three it is. So I'm going to take moments about there. That's kind of going in a clockwise way around this point. Therefore, this needs to be an anti-clockwise way. So it's going to be somehow in that direction. Now, the size of the arrow, the exact direction, I haven't worked out, but I know it's going to be in that quadrant, which is enough for me to then solve a problem on it. This one here, really similar to the previous one. Don't know vertical component, horizontal component has to be to the left. If I take moments about here, I know that it has to balance this anti-clockwise moment, so it's going to be clockwise, so it's going to have to be this way. Now, what you will notice with these two is that they're sort of symmetric, so you either have forces like this, or you have forces like that. And then you could have the reverse upside down. And that can sometimes help you just sort of quickly sense check what you have worked out. That concludes this video.